All right, so a very good morning to everyone who has joined today. My name is Sarthak Arora, and I will be the host for this webinar. It's 10 a.m., so let's just wait for maybe a minute, and then let's get going. All right, so let's get started with our webinar. Thank you, everyone, for joining this morning or afternoon or evening, depending where you are today. But thank you, and I hope you'll get to learn a lot from our presenter, Professor Prasad Kalyam. So before we jump right into the webinar, let me first thank Professor Prasad Kalyam for being here as the presenter and sharing his knowledge on the topic with us today. And before we jump into the webinar, I would like to briefly introduce Aquila Clouds. So Aquila Clouds offer an AI-based software as a service platform that provides full control of your cloud deployments across costs, performances, and security best practices. Aquila Clouds enables the paradigm of continuous monitoring, continuous optimization using our application intelligence, automation capabilities, and our closed loop approach gives visibility, recommendations, and automated actions to cloud operators for making them more productive. So continuing on that, if I had to give my personal perspective, I'd say like I have a very non-technical background, which is MBA in marketing, and then even my job experience has been pretty much non-technical. But when I joined Aquila Clouds, it made me realize the importance of automation. And if we talk about areas such as cloud computing and IT, automation is actually the key to success in the long run. And here at Aquila Clouds, that is exactly what we do. The tools which we have, they provide the automation for cloud operations so as to make them more effective and efficient. We also make sure that the clients we have get the best out of their cloud experience for a minimum cost. That is, we try to save them money while giving a better optimization for their cloud operation. And we make this possible by providing the right governance of the cloud operations, such as by giving better visibility, recommendations, and automated actions for the cloud operations. So if you would want to check us out, we have our website, www.aquilaclouds.com. You can find more information about us here. And if you can, do follow us on our social media handles. We have everything embedded in our website. We are on all major platforms, so you can follow us for all the latest information, updates, opportunities, and similar webinars like we have on today. So moving further, let me introduce today's presenter, Professor Prasad Kalyam. Professor Prasad Kalyam, he is an associate professor in the Department of Electrical Engineering and Computer Science at University of Missouri, Columbia. Having overpublished about 140 papers in various conference and journal venues, he is an expert consultant for the industry, academia, and government agencies in the design and development of software systems, comprising advanced architecture and cloud-based performance and security analysis technologies. So without much wait, I'll hand over the presentation part to Professor Kalyam.
Thank you, Sarthak. Thank you very much for that kind introduction. Yeah, I'm now the host. So
yes, you're the host now, and
share my screen.
yes.
Can you see my screen? Visible?
Yes, it is.
Awesome. Great. Thank you so much. Yeah, and it's a real pleasure to come back as a speaker for Aquila Clouds, and it's been a great few months learning more about all the success of Aquila Clouds and cloud computing. Is still the most important growing industry, and not everybody is an expert in cloud. So more companies like Aquila that provide ways for users to make it easy to use the cloud, the better we're all. So I'm really appreciative of all the work you're doing, and I'm glad to be associated with all the work you're doing also as advisor. And in this talk, I'm talking about edge computing, which is the next wave of cloud computing, but bringing the cloud closer to the user, or bringing the cloud closer to where the data is. And the kinds of things that generate the data are very different. And this is where we get into the realm of Internet of Things. We have sensors, devices, cameras everywhere in mobile, and in fixes across smart city platforms. So we have a different kind of an ecosystem, but the same cloud problems exist. There's a lot of data. There's a need to process it in real time. And there are people interested in different angles of the data, and they're all distributed. So how do we provide the right kind of analytics and control on these devices, so all the information from all these devices can be used for some very important things? That's what I want to talk about today. And the cloud is very much part of all of this, right? With edge computing, augmentation of resources, or if it's about having a cloud-based network control and security also. And the application I chose today for edge computing is drone video analytics. And this is a very exciting, emerging area, and there's a lot to be discovered in this area. There's a lot to be explored in this area. And if you are in academia, the drone video analytics or drone related computing networking publications, they're just exploding at this point. So this is really one of the trending areas, and it has direct relevance to cloud, AI, machine learning, and all the other things we think about in the traditional data center cloud computing sense. So I'm excited to share with you the work I've been doing with a wonderful set of contributors, and several of them are on this call. My PhD student, Chengi, Alicia, who just completed her master's, and many other PhD students who work with Dr. Pal, who's my collaborator, and some visiting scholars, Dr. Rao and all that. So I'm very much excited to share all the really great work of this whole group of excellent team members who contributed. And I've left some names out. Denise worked with Alicia on some of the things I talked about. And Jian Singh helps me, who's also on the call, with projects that could be using some of our work. So there's a whole lot of great people that have contributed to what I'm going to talk today. So what I will go through today is, excite you about, what are the possibilities of using drones or a network of drones, and how the idea of using a network of drones or the information from the drones can become an interesting edge computing problem. And cloud is definitely part of the solution, but new problems will come in how you do computation, communication, security. So I'm going to motivate all those kind of issues, and how we could start studying these systems that are just emerging. We don't have the cloud for drones. We don't have the edge computing paradigm set up for secure operation of the drones. All of these are emerging. So I've kind of outlined what are the challenges and give you a sense of what kind of solutions can be explored. So this is the work that Chengi is pursuing. We call it a drone coconut framework, which is drone computation, offloading, and control networking framework that is essential to orchestrate these drones. And in the world of AI today, we all want to see autonomous drone computation and networking and management. So how can we go towards that sort of a dream, right? And what kind of system design can we think about? We'll talk about that. And towards the end, I will give you some interesting test beds that we have built, edge computing test beds that allow us to answer very interesting questions about how do we do drone swarm autonomy. And we'll show you some results from our tests that show what are the potential benefits or what kind of configurations are very much promising to build upon to study various applications of this drone video analytics area. And I'll end the talk with some summary and things that we're doing right now. So to start from the beginning, this is the world we live in. If you see this graph where we have a collection, I call it a fog or edge, which is connected to a core cloud or a computation hub, where pretty much most of our application resources are today. And then there are people in a consumption fog, which is somewhere either near the collection or somewhere far away, where there are people who are interested in the data that's coming from the collection fog. And you can think of the collection fog as a place for disaster incident management. It could be agricultural use cases. It could be border security. It could be transporting packages to our homes at some point someday, and that's more of a use case now with the pandemic than ever before, right? The idea of package delivery is becoming very much the center of our lives these days. We're not going out as much, so there's a lot of things that can happen that's driven by devices that are mobile, that are constrained at the edge. But they generate a lot of data that needs to be processed, maybe at the collection side, but we can imagine those are places with austere network connections, limited computation, variety of resources. So the data has to go to a sort of a central computation hub, a core cloud, where all of the data can be processed at scale, at high speed, and the intelligence that comes out of it can be used for visual situational awareness. So people who are responsible for making sure public safety works or border security works, or the farming works, or a medical person gets like an organ through a drone flying with a organ for saving a life. Any of those use cases that we can think about, they are done effectively by the decision makers in the consumption fog, right? So this is the picture we want to paint of what's the future going to look like, where we will extend the cloud to these data collection fogs and data processing or consumption fogs, where decisions are made that have very much great impact. And all of this is going to happen on a sort of a geospatial footprint, right? Everybody's distributed, and there's going to be a lot of video, which is the biggest of the big data, right? So we'll have a lot of video that will drive how these applications function. So as I already told you, it can be a very interesting application, but it is pretty complex. So the idea of using drones or these unmanned aerial vehicles, we call it, or systems of vehicles that you can think of, they can come up with very, very interesting intelligence. So here we're seeing where you can take a large mosaic, right, of a city or farmland, and it can create a picture from multiple perspectives that's unlike anything we can imagine with technology today. And a lot of the people on this call are working on algorithms to create these sort of interesting, processed analytics that's using video data. It's using sensor data that's on the drones. You can have a variety of sensors that can go on the drones, and there's a lot of supporting services that guide the drone, that help coordinate drones amongst each other to achieve a mission, right? And all of that data processing is not trivial. It requires a complex set of pipelines that have been developed by the computer vision field for a long time. So how do we take these sort of known techniques and new emerging deep learning frameworks and new kinds of hardware, new kinds of sensors, and bring them together in a way that we can create these future systems, right? UAS or a fleet of drones that can help us to do better agriculture, so we can build better drought-resistant crops, or we can do border security at a very human aware way. You can do intelligent transportation, like I was talking of, maybe flying an organ for a disaster medical response, right, in time to save a life. So you can think of all these amazing possibilities. But obviously, these things come with challenges. Like I said, there's limited resources at the edge where all this amazing data has been collected. There are restrictions, by government about what you can and cannot do with drones. And then there is obviously the issue of how are you able to control and manage the orchestration of all these computation that needs to happen to effectively use these systems. And so the problem, we kind of break it down into two broad problems. One related to systems management or the software management on the end systems. We call it computation offloading. And the other is the networking between the drones and between the drone and the ground control station. So here you can see there are a number of drones. We can think of an application where we're considering a FANET, a flying area network, which has a number of drones that communicate with one or more ground control stations, and they form basically a UAS, right? A system where the ground control stations are coordinating with the cloud or amongst themselves to guide the drones, or in some cases do different things with the drones. They could be making them do video collection and analysis, or it could be just path planning to deliver different things from one place to another, right? So these are kind of broad application types we can think of, and a system model looks something like this. And the links, again, are constrained links from the air to air or air to ground perspective. You can think of them as Wi-Fi links or radio or IP links, and the technology that you use on the drones will determine the range, the resilience of those links. And the fact will be that these links will have intermittent connectivity. They are affected by obstacles, and energy is a major issue on drones, right? So there might be drones that need to come down because they're low on energy, and so the system configuration has a very dynamic topology. So managing such kind of a system requires you to really very carefully, intelligently manage the computation, what's going on either on the drone or on the ground control station or in the cloud, right? What needs to run where is a big challenge. So we talk about those problems as computation offloading. And I'll describe some algorithms we've been developing in that space. And the communication part of it is, how do we ensure that the mission is successful? We have a number of drones, we have a certain mission. In many cases that we consider in our research, there'll be hierarchy of drones. So there will be one variety of drones that might do a search across a wide area, and then there might be a completely different drone or a variety of drones that are more expensive that would do intelligence gathering, right? So you're thinking of these different use cases of search drones, hierarchical drones. So how are we going to orchestrate those and communicate, which drone needs to be where, right, to do the right kind of mission-specific actions. So the networking part also becomes a very important aspect. And as this is happening, we are assuming, the data can be processed, using real-time processing sometimes, which is important, where based on a certain snapshot of what the drones are seeing, maybe you need to change how the drones do the remainder of the mission, right? Or new drones need to go up and things like that. So the real-time processing is an important aspect, and we kind of focus on that. But you can also think about, the old ways of, the drone down, maybe swap out its storage and find all the data, drive it to a data center to process. So those things are what are happening today. But we have the ability, if we can come up with proper architectures of edge computing, we can automate these things. We can, like we were saying in the Aquila Cloud's context, we can bring a lot of AI kind of getting a little bit more technical, here is how we think about this computation offloading problem. What we do is we use this paradigm called as function-centric computing, where we imagine that a data processing pipeline has a number of functions or sub modules, or you want to think of it as microservices also, right? So things that you can have in smaller portions, but they specialize in those particular aspects, and then you can chain them. And this is called as also service function chaining. So we can take this idea of a complex workflow, break it down into a number of pre-processing functions or tracking functions or HCI analysis functions, and then we find a way to chain them, and that helps us basically place computation wherever it's relevant, wherever it's optimal, wherever it's more secure. And we can also make the communication much more dynamic. So if the functions are running in places where the resources are limited, we can use the networking to change where the function completes its task. Or if we find a function at a location where it's in a compromised situation, security wise, we can move that container, which has that microservice, to a different location, or initiate a function at a different place, which is dormant. So we can think of all these very intelligent, flexible ways of orchestration if we can imagine a world of function-centric computing. And this has been a very interesting exercise with my collaborator, Dr. Palace. How do we take tens of years of all these techniques that have been developed in computer vision, and the traditional paradigm of computer vision is we want to engineer the algorithm to the hardware. We want to optimize it for a particular hardware. We want to deeply couple it with the hardware so that you get the most performance. Whereas in the cloud context, this is the opposite we want. We want the ability to decouple everything, have it be modular, so we can be more intelligent in placing and managing this set of functions. So we wrote a whole book chapter that is available that details this whole idea of function-centric computing. You can read that. And ultimately, we want to study these kind of problems with a low cost and at a high scale, right? These ideas are very interesting, but how do we show they are essentially, providing the benefits we claim, right, in terms of time or cost and things like that. So to study these systems that today don't exist in the market, in the sense that you don't have a product that actually sells you how to do drone video analytics at a large scale, right? So you are studying these systems, you're building these systems. So since they don't exist already, how do we know how to build these and control these? So we use a combination of simulation and experiment, and that's part of our approach. Is how do we create models of these systems, imagine what kind of adaptations or policy experiments we can do on these systems, and how do we create new architectures like this microservices paradigm for doing this edge, ground, and cloud orchestration, right? So these are problems that have to be studied, and these are challenges that we're trying to address in the research. And the challenge also is, as I said, you need simulators to study things that don't really exist in realism, or if you want to mimic what is real, but at a very low cost, high scale environment, you use simulators. And if you look at the history of simulators, there's a lot of network simulator platforms that you can use. NS3 is a very popular one, but there are very few drone simulators. So there's different groups coming up with drone simulators that are also kind of getting interestingly useful. But there are no simulators that integrate both of these. So in our situation where we want to study the drone computation, offloading, and control networking, we need to really create something that doesn't exist, which is bring the benefits of UAV level simulators and network level simulators into a more unified simulator that can be used to answer some of these questions I was talking about, right? From a computation offloading perspective, also from a networking perspective, to study mobility and video control protocols as the drones are collecting video from the data. And the problem of the networking, we look at it as a codec selection problem. So at what quality or frame rate can the data be transferred? And as I said, considering some kind of real-time use cases where the ground control station needs to have some idea of what's being collected on the drone, right? So you're trying to communicate this information between the drones or from the drone to the control station. And in the networking context, we call this as the transport protocol issue, right? If you think of your mail, you're writing a message, you're putting it in an envelope, and the next part is, taking it to the destination, right? And we have TCP that's requiring confirmation. UDP is more connectionless, right? So you're trying to make sure that message reaches, then you have to use TCP. If you're just trying to send the message without worrying about confirmation, you're using UDP. But those were the traditional protocols, but more and more what we have found on the internet is protocols are very specific in terms of transport for different applications. And so the protocol that's been kind of very popular in the recent times is this QUIC protocol. That we have actually been exploring in conjunction with TCP and UDP. And we want to understand what kind of right codec selection improves the video analytics. And it helps us deal with this mobility of all these drones, in the field, right? And we want to be able to predict the right protocol and the right setting of the application transport protocol to make sure we get the best frame rates, the best tracking times, and all these benefits at the application level, right? If you're doing a fusion and tracking model, for example. So you want the tracking speed to be high, you want the accuracy to be high, you want the frame rates to be high. And so to get these benefits, how do we do some predictions? And so this paper, Rumana is here, and we've been expanding that work. We are imagining how we can take these transport protocols like QUIC and make it quicker. It's kind of a cool name we came up with, where we can parallelize some of these transfers based on the end system requirements, the video transfer requirements, and we can create better function chains that are more efficient. Or in the second picture we're showing here, how can we use some kind of a method, and in this case we're using some machine learning to figure out what is the right kind of resolution, codec selection, transport protocol selection that we can use to transmit the video over a given network link. And last but not the least, as we're building the systems, they're going to be doing very important things, like I said, maybe life-saving, life-changing things. And it could mean that, there is a new architecture that we come to put in place for these systems. And anything that's new, it's not well understood, is prone for attacks. Either it could be inadvertent in the sense that there's a user who's doing things that they don't really understand, that could lead to some of these cases where it looks like there's an attack, or basically a mission is disrupted, right? Or it could be somebody who's actually malicious, who's doing things, in terms of, integrity, confidentiality, availability, that's impacting your mission. So there are a lot of works that are starting to look at how do we do this, computation offloading and the communication in a secure way. And our work, which is recent and led by Alicia and Denise is here, and a group of people, we've come up with this idea of how do we think about the types of attacks that can happen in a drone context, especially if you have multiple drones. And like we talked about, we're talking of search drones and intelligence gathering drones. And there's basically data at risk, either in a static sense or even in a dynamic sense, right? So we have considered man-in-the-middle attacks or things that could be around stealing or disrupting the data collection on the drones. And considering the sort of the container microservices paradigm, in this work we've been exploring how can we create better encryption for some of the protocols that are used, like Mavlink in the drone context. What are the issues in terms of putting different kinds of security design principles to make sure that these systems can be more resilient to say jamming attacks or spoofing attacks or basic denial of service kind of attacks. So this is all new work, but again a very important problem, and there are new challenges if you're dealing with the security and privacy aspects of these drone swarms. So with that, hopefully I've excited you about all the possibilities of UAS or drone swarms, and given you how we can bring sort of new perspectives on real-time control or cloud integration or just managing the complexity of what needs to happen to achieve different kinds of missions, right? And so now I'll quickly dive into some of the solutions we've been thinking. I gave you some hints of ways we can think of this problem as an edge computing problem that has some cloud flavor to it. But what exactly can we be doing in terms of machine learning and building this kind of platforms to test and deploy these kind of systems, right? So, so the framework that we're building, which is led by Chengi, who's a PhD student, and he's been doing excellent work in leading a lot of efforts that go into the computation offloading. Like I said, how do we make dynamic decisions of where the computation has to be done on the drone or at the edge, or needs to be offloaded to the cloud, and what goes into deciding, right, where, when, and how to offload the computation. So there are problems that he's been tackling on that aspect. And in the control aspect, like I said, it's about figuring out what kind of transport protocols are needed, what kind of video codecs make sense, and how to deal with issues of mobility, energy, latency issues from a network controls perspective, and what algorithms we need for the control part of the drone swarm. So he's looking at that. And then the application aspects, for drone video analytics or path planning, the routing, the task scheduling. So all of that assisting the application needs to happen. And that's part of the FANET functionality. And this is a kind of a funny acronym. Also, we found this cartoon of Serena Williams, right, using what looks like a coconut to hit the drones. So if you are on target, if you can control the drones, and hopefully that drone is a, compromised drone or a drone we don't like anymore, right? So I'm just making fun of this. But the idea is that you could control the drones, and drones are a kind of interesting, end device that has interesting networking challenges and computation challenges that we can solve through this kind of framework we're developing. And so this framework has a number of features that I kind of said are missing in today's research or state of the art. We really want to understand multi-drone edge server architectures. So there's very few works on that. So we've been studying new architectures. We also were looking at different application scenarios. What could be the application scenarios we looked at in our lab, at least? Public safety for protest incident management. We've looked at some kind of border security issues. We're starting to look at agriculture kind of issues. We've looked at medical triage and disaster issues. So there's many application scenarios, and each scenario has a different, use case and system design issue that comes up with. But to be able to study these systems in a systematic way, we've been looking at integrating both, the drone simulators, network simulators, also integrating simulation and real experimentation. So running actual drones in the field, getting some traces from the drones and putting them in a simulator where we can change the variety of mobility models or the pipelines that have different, say, latency requirements. So you can do a lot of experimentation without having any impact on the realism or the scale that would limit us in a realistic sense, right? So we could do these things. So how are we able to combine these simulators and synergize experiments and simulation? So we are working on aspects of that in the drone coconut. And we're also looking at different configurations, different types of platforms of drones, different network technologies that exist there that can help with these drones, protocols that help with these drones, and also what's the aspects of security that we can also study, and what kind of test beds we need to study them, right? So these are all part of the drone coconut framework studies that's been going on. I'll give you a little bit more details in this talk also. So at a high level, here is the system that we are building, or we're thinking about in terms of different problems we want to solve. And the way we think about it is there is a secure real world environment, right? That's actually collecting all the data, the traces with different sensors or video or mobility models of the drones. And we can get some amount of information. It's limited by scale or cost that we're able to afford to do these things. But we can get a significant amount of real world information. And we want to bring that into a sort of an environment where we can have repetition, right? We can do repeatable experiments that are guided by the real world, but also have the flexibility to meet different application requirements. And so we're not constrained by the realism in really figuring out what's the right deployment for an application. And the system for the simulator is around data analysis and learning. So it's a dynamic system. So it has to be updated as we have new knowledge, and it has to be powered by a number of algorithms that can be plug and play, right? So we want to think of these as apps that we can put to say, I have this mobility model, what do I do? Or I have this kind of application requirement for video processing, what do I do? Or I have these set of computation resources, what can I do, right? So, or these are the security requirements, how can I build a system that does, a certain, application specific task scheduling, and how do we, make that optimal and things like that. So to come up with all of these solutions to different problems we want to study, we think of this as a hierarchical. So we want to think of multiple drones or a hierarchy of drones. We want to use it as a trace-based system. So we want to have realism, but also we want to have a simulation platform that's combining the benefits of a UAV simulator and a network simulator. And we want to be able to use machine learning to do different use cases of geospatial video analytics. And these days, we're also looking at path planning also, right? The other application I talked about. And a little bit more on the three aspects, right? So we want the traces to have all the data that you would collect if a real drone flies, like coordinates, the device it was on, the duration of the flight, proximity to certain, locations that we are of interest. So things like that, we want to bring all that metadata, right, as part of the traces into the simulator. And we want to have also some network aspects of the system. So again, we might go to a real experiment testbed and go like, for this kind of a communication and these sort of wireless channel limitations, what's the throughput I can get and what's the frame rate that's feasible. So I want to be able to get all that kind of data that I can then use to create some analysis of the task area or the flight plan or the communication network support, and then train my models, right? So I can learn and create these algorithms that can help with selecting the network protocols or flight paths or predicting where the wireless signal would be great for the drone to really, have a path towards, right? So, and the machine learning part, you might be wondering, why is that relevant here from a drone video analytics perspective? And we have found that, this could be an overwhelming problem if you have many drones. There's a lot of metadata, there's video, there's a lot of dynamism in the environment. So it does provide this sort of a problem where there is a lot of data and we need machine learning models to do the estimation. So the kind of traditional estimation methods might not be sufficient to provide. And we have published papers to that extent, showing that machine learning methods do better than just sort of straight estimation. The end goal is, as I said, picking the right protocols, the encodings in the protocols, finding the right locations to do the processing, right? And we've been able to collect in our papers, and some of these data sets are also available, that shows how we're able to take this data and do a number of machine learning kind of tasks. And how we actually do it is, we have the training, we have the testing, and there are public drone traces that we're using. There are traces that we have collected. And so we're increasing this database that we actually use in our experiments, and we're able to test the accuracy of different machine learning models to pick the right schemes that we can use for estimation of performance or security anomaly events, right? So this is something that's ongoing. And the framework, like I said, is obviously a very critical contribution, and how it's actually set up with different test beds is where really the benefits of the framework are there. And so we have been working on a variety of test beds that are not your traditional test beds, but are interesting new ways of thinking about how we can make these experiments repeatable. So here we're showing a test bed for how we can use drone traces in a network simulation context. And we can actually study a number of things related to the video processing, or different characteristics of flying these drones in different environments. And so we have gotten some traces from a group in Portugal. There's some work we've been doing with this emulator that's from University of Buffalo. So we've been building upon some of these open source codes and trying to put them together to provide a framework that works for us in Drone Coconut that synergizes drone and network simulation. And also we've been looking at new test beds where we can build more realistic edge cloud test beds using open cloud. So we're using the NSF cloud, which includes Cloud Lab, Genie, and other kinds of resources. And there are racks of those across the country. And we have the Missouri Genie rack here, and we are using other Genie racks. And we're thinking about, deploying these interesting pipelines that are used, very commonly for a lot of the deep learning stuff that's used for pattern recognition, doing a lot of classification of objects and things like that. So we've been able to use these pipelines successfully in the function-centric paradigm. So we've been able to deploy these as, containers in a cloud edge setting, create more realistic workloads and study, like I said, frame rates, tracking times, and all those things. So, so we have, again, these experiments and data published and some data sets available. And more recent work that Alicia and Denise and others are leading relates to bringing these wireless test beds and the simulators, which in networking we call NS3 simulator, together. And how do we set up these very new kinds of environments that have not been studied, so we can actually answer very deep questions. How does, say, a wireless channel issue affect the QUIC transport protocol configuration? So a lot of that today is assumed, and we don't have real empirical data or a way to validate some of these assumptions in current test beds. So we're building these new test beds where we can really go and do very interesting things that are configurable, that are repeatable, the software in the loop, and we can evaluate many different things. So in this case, we are actually looking at security issues. So which kind of encryption protocol provides the least overhead with the best security. So that could be, for example, studied. And Alicia and group looked at how you can run a encrypted reliable UDP socket between the simulator in NS3 and an actual wireless testbed node, right? And using the Mavlink protocol that's commonly used, how can we achieve a mission of understanding how do we send communications between the simulator and the edge server, right, in the real testbed, but also how do we, for example, study security issues. So one of the things that they studied was, can we use this kind of testbed to figure out how to build dynamic trust? So can we actually trust a drone to do a certain mission critical task? And if there are issues with the drone, either malicious or there are events in the drone that reduce the trust or the reliability of the process, then can we migrate the responsibility to other drones, right? So we're looking at this model where, again, we're using machine learning to identify these anomaly events. And we have this container architecture where we can, for example, if you find a drone that's malicious, we can, pause the execution there, and then we can come up with a way to activate a container at a different location to continue the execution. So we've been exploring these sort of interesting paradigms, and the zero trust and other aspects could be, again, hypotheses that could be used to see if we can improve the security and privacy of drones. So coming to the last part of my talk, a few interesting results. So we've been able to successfully do this, and Chengi has a lot more information if you want to actually learn about some of our experiments, is how we can use these drone traces to come up with different scenarios of a number of different UAVs running, and how the video transmission, for example, using the PSNR, objective video quality metric, we can study how these architectures work. We've also been studying, as I said, the comparison of different transport protocols for a particular sort of video transmission use case, and how we could see what is the effect in terms of frame rates, latency, and things like that, right? So we can study issues related to picking the right transport protocol for a particular application. And also looking at how the information that we get from these systems, and Alicia has been developing this interface, can be very useful to see, having a sort of a more unified interface to control, inspect, and manage these simulations and experiments. So that's something, again, which is being developed, which has, again, a lot of benefits for many others. So in summary, what we have done is really look at this problem of drone video analytics in a sort of a cloud edge context that's new. Not many groups are doing it, and we're fortunate to be funded through NSF and Army Research Lab to study these with a great group of people. And we have tried to bring realism, high scale into our experiments with drone video analytics, and that basically meant bringing traces from real worlds, bringing simulator models from very established simulators, and really integrating them all together, the network simulators, drone simulators, and these traces to study different questions on computation, offloading, and control networking, considering the mobility of the drones or the geospatial link information and sort of the real-time requirements of the applications from the network perspective. And we've been able to show that machine learning models can be very appropriate and useful in the process of creating the new system designs, and definitely new architectures are emerging that require hybrid test beds with synergistic connections in the experiment and in simulation, and also thinking about how we can make use of open data sets, different kind of hardware node types, the communication technology options that are out there, and how do we put them together to make them customized for important applications in farming, agriculture, public safety, medical triage, and things like that. So that's been what's been driving us, and we're continuing to build. As you saw, there's a lot of potential for new problems to be explored in security, mobility, And our ultimate goal is how do we get to the point where we are able to confidently do autonomous drone swarm studies, right? And this requires a lot of control theory, cloud computing, optimization, and so all of those things are something we've been working, and we're expanding our collaborations with people who are developing the right kind of simulators that can help us in creating the drone coconut, and also the test beds like wireless test bed like powder that allow us to really bring the realism of the futuristic wireless platforms, right? Advanced wireless platforms as part of our framework. And we want to really bring our own nodes, for example. So we want to have a realistic node at Missouri that can have a, like we talked about, this real world trace generation capability that can be brought into these reproducible test beds very easily. So it takes a lot of effort right now, but we want to make it easy in the future. So with that, I conclude, and I'm happy to answer any questions on anything that I've said. And as I said, we have been fortunate to have funding from Army and National Science Foundation, and there's a great group of students, many of whom are on this call, who have contributed to this work that I presented.
Awesome, Professor Kalyam. Thank you for sharing this vast amount of knowledge here. And it's great to hear all of this research has been funded by the research labs. So I think it's really exciting to hear that. And I'm sure there's a lot of prospects and scope in this research. I do think this topic has a lot of relevance to a lot of practical usage, such as drones have taken such an important part in our life, from say fascination or the idea of delivering Amazon packages through drone to helping firefighters fighting or containing fires and all of that stuff. It's a really practical topic, and I'm glad I was here to learn all of this from you. So like Professor said, if there are any questions, please feel free to either ask them. You can turn on your microphone on, or you can also write your questions in the chat box and I can read them out to Professor.
Hi, Dr. Prasad. This is Akinjan. So I really like to first appreciate your work. I was actually fortunate to watch, observe this work by distance thanks to Denise. So my question was about the edge server side, the security. So as I remember from the RU project that you've done this semester, so you have some security measures to prevent any kind of attacks that comes from the drone side. But I was wondering that if there's any kind of security or safety measures that is taken on the edge server. Like, I'm trying to come up with an example, such as you already have this beautiful system that manages and coordinate these drones to collect these, to do video analytics. But what if I just hack into this edge server and I actually use it into my advantage to redirect them to another place and collect information that is not supposed to? So I was wondering if there's any kind of security measures for this.
Oh, that's a great question. And, I'm actually teaching a course on cyber defense where this is what we talk about. So this is kind of a new system, and you're given, all these benefits of the system, and you have different assets like I talked about, right? The edge system, the edge server, the cloud, and the protocols that are in place. So you have all these assets from different layers. And what you asked me is the golden question is, how do I create a threat model? And like you pointed out, the trusted computing base, or sort of the core of the control, is in this edge, server that seemingly connects the cloud, which has this infinite resources, which can be easily compromised if the edge is hacked. And again, compromising the edge server can absolutely do notorious things on the drone side. And so that becomes a very nice target for somebody who wants to launch an attack, or that's a nice target where if you are not doing the right kind of things, even if it's not malicious, you might do things that are threats that essentially hamper your mission. So what you're asking is a question that we study where we say, you know, how do we model the threats? How do we model the impact of these threats? And how do we model the risk of these, right? And so this would be a very interesting exercise that actually we're doing as part of this course is, you know, how do we categorize, you know, different kinds of threats as, you know, what's the risk and what's the reward, right, for somebody doing it. And for us to come up with defenses, right, in the case that you talked about in the RU case, encryption on Mavlink is a very good security design principle. So that by itself is very simple. It doesn't require a lot of management. If the encryption is managed properly, the key stuff and all, then it's a very good way to avoid loss of confidentiality. And it's an open standard, so everybody knows all the, you know, if there are any vulnerabilities, they're patched, and, you know, there's sort of a security openness, open design in place. So that's a good way to create a solution, right? So now what you're asking is, what are the right solutions at a server side to make sure that the threats and the likelihood of the attacks are minimized. So again, there are many solutions, and the way we think of it is, you know, automation wise, API and middleware. So that's what would be one of the ways you can improve the security on the server side is you restrict or isolate the functions that are critical and provide, you know, as much as needed, least privilege, you know, access options to users. So the operations or the type of operations you can do on the edge server are contained in a, you know, sort of a managed privilege space, right? So you don't give away privileges on the server, you know, by default, things like that. So there could be a number of things you plan around, and you know, that's what we're working on these days, is what kind of security principles will work and how do we validate those principles actually, you know, don't make it harder for the user, or, you know, sort of open up other you know, issues of vulnerability. As we're trying to defend, we might bring in new vulnerabilities. So that's a study we are actually still pursuing, but that's a great question. And what you asked is exactly the kind of you know, a cybersecurity engineer you know, question you do when you're given a new system like this.
Thank you very much. I really appreciate the answer, and you and your team has done a really great work. So thank you for that.
Thank you, Professor, for answering the question. Do we have any more questions, sir? Okay, looks like it. We're all done. Before I let you go, Professor, I had this question because I am physically located in Southern California, and because there are so many wildfires we see in the news that there are going on, and see how tough it is for firefighters to fight in such heat and in such circumstances. Do you think that incorporating such technology with drones can help in you know, better understanding the situation in such areas and give a better understanding of what kind of fire is going on, what's the, you know, what's the best strategy to tackle, and how can it help to contain such natural disasters like more easily and more effectively?
Yeah, I mean, that's a great question. I mean, you're asking something that's really the kind of futuristic application for these, you know, concepts that we talked in this talk. And the question is a great question. The answer is a little bit philosophical in the sense that, you know, the reality of the situation is, you know, the public safety people, you know, they are already fighting the fire. They don't have, you know, the technologies or infrastructure in place to really worry about automation or orchestration. I mean, this is sort of the practical problem of public safety is they're typically not, you know, very much in step with technology. And again, technology is not very much in a place where it's usable by these people in different scenarios, right? So the human method works somehow more effectively than technology, but that doesn't mean the technology has no benefit. So, you know, part of what I see as a solution is, and this is a problem that's been studied for tens of years. So people have thought about UAVs in fire, you know, search and rescue and other kind of situations for many, many years. But it's more promising today than ever before. But a lot of this technology comes with, the right kind of training, the right kind of preparedness. And as I said, each of these have mission specific configurations. There's no one out of the box solution that will work for any of these scenarios. And so there is a lot of research that's going on, which will hopefully get us to a point where we can hear more news that all these firefighters use this kind of technologies and they were able to have a lot of benefits. We don't see that kind of news very much in the forefront, but I believe there are it's kind of cloud-like principles using kind of templates for different kinds of missions where you can maybe come up with customizations just like we're doing in the cloud, right, to automate a lot of processes, coming up with templates that can help different scenarios in which the firefighters want to deploy, again, the benefit of this technology. And so there's a lot of work that's going on in the public safety space in terms of using virtual reality, where they can use these technologies and actually experiment them. So some of our simulators that we're doing for research also could be turned into sort of training simulators for firefighters to design a kind of a configuration that might work for what they're trying to do. But like I said, there's a big gap in terms of where the technology is and where it is actually usable by the people on the field, and that this technology is commercially available, it's resilient, it's robust for the task, and it's able to meet the different requirements or customizations, right? So there is a gap, and unfortunately the public safety industry is not the same as the gaming industry. There's not like a huge demand, because disasters happen, but they happen at a certain frequency. That doesn't mean there's a mass market for it, but we are all very much invested. There's a lot of government funding and there's a lot of groups that are trying to bridge this gap of technology and usability and trying to bring the real field people to embrace and use them in real scenarios. So I think we will see more progress. The number of disasters, unfortunately, is only increasing every day. And there's a lot of great research that's going on. And I hope that in the near future, we will see more press releases that technology saved the situation than we have today.
Yes, thank you, Professor, for answering this. I'm sure in the future we'll get to hear more of use of such application in the real world, and I hope that such technologies save more and more lives in the coming future. So with that, I would like to thank everyone here today for attending our virtual webinar. And we would have a similar webinar 2 weeks from now. And that would be more on billing operations with cloud industry. So if you would want to join that, please feel free to join that. I would be posting information about that on our social media pages. So please feel free to join us or follow us on our social media platforms. We are, like I said, available on all the platforms. If you go to our website, www.aquilaclouds.com, you'll find us, you'll find all the social media handles. With that, once again, thank you so much. Stay safe and hope to see you next time. Bye-bye.
Yeah, thank you. Thank you, Sarthak, for hosting.
Thank you, Professor. It. Thank you, Professor. My pleasure.
See you. Take care. Bye.
Take care, Professor. Bye-bye. Thank you.